Every transaction, password, and email we send online is secured by mathematical locks.
But a new threat is rising. Quantum computers, utilizing the bizarre laws of physics, will soon be strong enough to crack all modern encryption. Today, we are exploring lattice-based cryptography, the quantum-proof mathematical shield designed to keep our digital world secure.
Modern internet security is built on a foundation of prime numbers.
Systems like RSA protect your data by multiplying two massive prime numbers.
A standard computer would take trillions of years to guess the factors. But quantum computers do not process data sequentially.
Running Shor's algorithm, they can factor these numbers in seconds, breaking all web security.
Classical computers use bits that are either 0 or 1, scanning combinations one by one. Quantum computers use qubits that can exist as 0 and 1 simultaneously.
This allows them to scan all combinations at once, solving prime number factoring instantly.
To secure our data, we need to design new locks that quantum computers cannot pick. The solution is lattice-based cryptography. A lattice is an infinite grid of dots created by repeating vector patterns. In 2 dimensions, a lattice looks like a simple sheet of graph paper. In 3 dimensions, it looks like a scaffold.
But mathematically, we can create lattices with hundreds of dimensions, which is where we hide our secrets.
Lattice cryptography works in 3 steps. First, a complex, high-dimensional lattice grid is generated.
Second, a secret point is chosen on the grid, and a small amount of random noise is added to displace it slightly off the dot.
Finally, the displaced point is made public. To decrypt the data, a computer must find the closest grid point. Finding the closest grid point is called the closest vector problem. In 2 or 3 dimensions, it is easy to solve. But as you add dimensions, the complexity explodes. In a 500-dimensional lattice, there are too many directions to search. Even a quantum computer gets lost in the multidimensional maze, making the lock unbreakable. The primary mathematical framework is called learning with errors. It hides secrets inside linear algebra equations and injects tiny errors into each one. Without the private key, these errors compound, making the equations impossible to solve. Quantum computers cannot bypass this noise, rendering the encryption secure.
The security differences are astronomical. While a quantum computer can factor a standard RSA key in 10 seconds, cracking a lattice-based key would take 1 billion years.
The trade-off is that lattice keys are larger, requiring more data bandwidth, but they guarantee absolute safety in the post-quantum era.
NIST recently completed a 6-year search for post-quantum standards. They selected a lattice-based algorithm called Kyber, now known as MLKEM, as the primary encryption standard, along with dilithium for digital signatures. Tech companies are already integrating these standards into browsers and apps.
Rolling out new encryption is a massive task.
We must update millions of servers, browsers, and devices globally. This transition must be completed before quantum computers reach scale.
Apple has already deployed post-quantum cryptography in iMessage, showing that the transition is active.
Ultimately, lattice cryptography is about preserving digital safety. It guarantees that our banks, power grids, and medical records remain private, even in an era of quantum superintelligence. By securing our digital foundations today, we protect the privacy and freedoms of tomorrow.
Lattice-based cryptography is securing the digital foundations of human civilization against the quantum threat. By hiding our secrets inside multidimensional lattices, we can run a secure internet for generations to come. What do you think about lattice cryptography? Let us know in the comments below.
If you want more simple science explanations, subscribe to Layman's Field, bringing knowledge for everyone.
We will see you in the next video.